Good morning. Welcome to this fourth lecture of the course Compressible Flow. So in the previous lecture we have started recapitulating the concepts of basic thermodynamics. Today also we will continue from the for the same. So if you do remember, then we have stopped at the point of thermodynamic property relations, where I had given first thermodynamic property relation as TdS minus say it was in the specific form TdS minus PdV is equal to du. This was the first thermodynamic property relation, and second property relation I had given as dH equal to TdS plus VdP. This was the second property relation. Okay, so now these property relations, because as I told you, what it does, it represents the complete equation in the form of all thermodynamic properties. For example, in first equation we have temperature, entropy, pressure, specific volume and internal energy. So all are nothing but the thermodynamic properties. Similarly, we have thermodynamic properties in the second equation. That's why we call these as thermodynamic property relations. Now we will try to utilize these relations to find out the entropy change during a process for calorically perfect gas. So the meaning of calorically perfect gas is, so let me once again repeat it. So the meaning of calorically perfect gas is that its Cp and Cv are constant. Okay, so if I consider Cp and Cv constant, then I can write du equal to Cv times dt, and dH I can write Cp times dt. Now using these formulations for a calorically perfect gas, equation 1 becomes, say ds equal to, what I am doing, I will divide throughout by t, and simultaneously I will bring all other terms to the right hand side. So I can say du as Cv times dt, and throughout I have divided by t. Okay, and this PdV on the right hand side, it will become positive, so plus PdV by T. Now calorically perfect gas is nothing but an ideal gas, or I can say a perfect gas. So for a perfect gas, we also know from ideal gas equation that PV is equal to RT. Now from this I can say that P will be equal to RT divided by V. So now I will make this substitution also to this second term. So from here I will get ds equal to Cv into dt by T, plus in place of P, if I write RT by V, this T will be cancelling. I will be getting R by V into dV. Now this is the equation. Say now if I integrate this equation from limits of state 1 to state 2. So basically the meaning of state 1 to state 2 is that we are having certain process, and calorically perfect gas is changing its thermodynamic state from point 1 to point 2 during that process. Okay, so what I will get now, you know that this Cv is constant for a calorically perfect gas, and R is also characteristic gas constant. So what I can do, I can take these two terms outside, and integration on the left hand side will become ds will become s, and in the limits of 1 and 2 I can write s2 minus s1. Cv I had taken constant. Integration of dt by t will become ln. So and limits of integration are t2 by t1. Similarly, plus r dv by v integration, I will get from here second term, r is constant, integration dv by v will become ln, and after substituting limits of integration I will get ln v2 by v1. Okay, so this is one important relation. So if a calorically perfect gas goes through certain process and it changes its state from point 1 to point 2, then this is how I can determine its change of entropy. Okay, so over here change of entropy I have established as the function of its temperature and specific volume, because Cv and R are constant over here. So I can simply say that S over here is simply a function of its temperature comma specific volume. Now similarly I can use the information of the pressure. Say if I don't have the data of volume and I have the data of pressure along with temperature, then also I can determine its entropy. For that what I will do, I will utilize this second property relation. So from the second property relation, if I keep this TDS on one side and take this VdP to the other side, then I will get and substitute dH with Cp dt, then I will get T times ds equal to dH means Cp dt minus Vdp. Now using the same ideal gas equation PV equal to RT, I can write that my V will be equal to RT by P. So let me divide throughout by T and substitute this specific volume also over here. So I will get ds will be equal to Cp divided by T into dt minus, in place of V I can write RT by P, and I am dividing with T also, into dP. So from here I can simply write that integration of ds from 1 to 2 equal to Cp, I can take outside integration, dt by T 1 to 2 minus R will be constant, T is cancelling out, so integration of dP by P from 1 to 2. Okay, so this will give me S2 minus S1 equal to Cp times ln of T2 by T1 minus R times ln of P2 by P1. Okay, so this is the second equation for entropy change of a calorically perfect gas during a process. Now the important point is, here you can see that entropy is becoming function of temperature and pressure. Okay, so one interesting thing to note over here is that we have seen in the previous lecture that internal energy and enthalpy of a calorically perfect gas are nothing but the sole function of temperature, whereas the entropy of an calorically perfect gas does not follow the same behavior. So in place of only a sole function of temperature, it is actually function of at least two independent intensive properties. So that is what we have done over here. In first equation we have represented entropy as the function of temperature and specific volume. In second relation we have represented it as the function of temperature and pressure, considering that Cp, Cv and R are constant for a calorically perfect gas. Okay, R will be always constant. However, if you are not having calorically perfect gas, then Cp and Cv may become functions of temperature. Okay, so now we will try to utilize these two important relations to determine the property functional relationships for the isentropic processes. Okay, so if you do remember, I have told in the previous lecture that isentropic process is something where we have nothing but ds equal to 0. So the meaning of ds is equal to 0 if process is undergoing from through state points 1 to 2, then I can simply say that S1 is equal to S2, and using the correlation ds equal to generalized correlation ds equal to del q by t plus delta s generation, this ds will be 0 if I say I have a reversible process. So if my process is reversible, then what will be happening? For a reversible process, delta s generation will become 0. And if I say I have idea adiabatic process, then del Q by T will be 0. So sum of 0 plus 0 will be 0. So what I can say that all the reversible adiabatic processes are nothing but the isentropic processes. So it means I can simply say all reversible adiabatic processes are isentropic, whereas the converse of this statement is not true. So I cannot say that if a process is isentropic, then it has to be reversible adiabatic. Okay. For example, if you want to maintain ds equal to 0, so you can have a situation where heat is going out of the system. So if heat is going out of the system and this is going out of the system in such a way that the del q by t is becoming, say, minus x. X is some quantity over here and it is becoming minus x. Now we have some irreversibility also with the system. So we have some irreversibility also. Okay. And this irreversibility is such that it is generating plus x amount of entropy. So what I am saying, here I have heat rejection. Heat is going out of our fluid for which we are measuring the entropy change. So heat rejection is taking place. So due to the heat rejection, say our this will be having negative sign because heat is going out of the system, and say this del q by t is having magnitude of minus x. Okay. And similarly, this delta S generation, because of the irreversibility it is generating, and the amount of entropy generated is equal to delta Q by T over here. So in this situation also I will get my left hand side as 0. So the meaning of left hand side 0 means we have nothing but the isentropic process, but it has irreversibilities and it has heat transfer. So it means all the isentropic processes may not be reversible adiabatic. Okay, but over here in our present formulation of compressible flow, whenever we will be referring to the situation of isentropic flow, majority of the time we will be nothing but pointing towards the reversible adiabatic flow. So let me repeat once again, though all the reversible adiabatic processes are isentropic, but all isentropic processes may not be reversible adiabatic. However, whenever I will be using this keyword isentropic over here in this particular course of compressible flow, so majority of the time our situations will be nothing but reversible adiabatic. Okay. Okay. So now let's try to utilize these equations. Say this is equation number 3 and this is equation number 4. So let's try to utilize equation 3 and 4 to drive the relation for nothing but the isentropic process. Okay. So as per equation 3, if I have isentropic process, then S2 will be equal to S1 and S2 minus S1 will become 0. So from the equation 3 I can say that this is my equation 3, CV ln T2 by T1. So I can say that CV ln T2 by T1, that will be equal to this term I can take to the other side and it will become minus R ln V2 by V1. Okay. So from here now if you take the CV to the other side, then you will get ln of T2 by T1 will be equal to minus R divided by CV into ln of V2 by V1. Now this what I can do, I can write ln of V2 by V1 to power minus R by CV. Okay. Now we know that R is for an calorically perfect gas, we can say that Cp minus Cv is equal to R. Okay. So if I calculate R by Cv, then I have to throughout divide by Cv. So Cp by Cv minus 1 will be equal to R by Cv. This Cp by Cv is an important parameter which is called as, say, gamma, and gamma is nothing but ratio of specific heats. So what I can do over here, I can simply write that R by Cv is nothing but equal to gamma minus 1. So from here I can say ln of T2 by T1 equal to ln of V2 by V1 whole power minus of gamma minus 1. Okay. Now I can take anti-log on the both sides. If I do so, I will get T2 by T1 equal to V2 by V1 power minus of gamma minus 1. Okay, so this is one important relation which I am getting over here, and is this point clear? So say this is my equation number 5. Okay, now the way I have taken equation number 3, similarly I can take equation number 4. If I take equation number 4 and make S2 minus S1 equal to 0 from equation number 4, so from here I will get Cp into ln of T2 by T1 equal to R times ln of P2 by P1. Okay, so from here I can get ln of T2 by T1 equal to R by Cp times ln of P2 by P1. Now R I will write, let me once again calculate Cp minus Cv equal to R. Okay, and here what I will get, if I divide by Cp, then 1 minus 1 by gamma equal to R by Cp. Okay, so from here I will get gamma minus 1 by gamma equal to R by Cp. So let me write it as ln of P2 by P1, and this I will take to the power, and in the power I will write in place of R by Cp as gamma minus 1 by gamma. Okay, so from here I will get T2 by T1 equal to P2 by P1 power gamma minus 1 by gamma. So this is another important relation which I have actually got over here. Let me number this as equation number 6. Now the interesting point is, in case of equation 5, I have got T2 by T1 as V2 by V1 की power minus gamma minus 1, and here I have got T2 by T1 equal to P2 by P1 gamma minus 1 by gamma. So from equation 5 and 6 I can say that, from equation 5 and 6 I can say that T2 by T1 equal to P2 by P1 power gamma minus 1 by gamma equal to V2 by V1 power minus gamma minus 1. Okay, now this V over here is nothing but specific volume, and we know that specific volume is 1 by density. So if I have to write this relation in the form of density, then if I use V2 by V1, so I can write V2 by V1 power minus gamma minus 1 equal to, this will become rho 1 by rho 2 minus gamma minus 1, and ultimately I can write it as, if I just take the reciprocal, then I can write rho 2 by power gamma minus 1. Okay, so this is simply, I can take the reciprocal over here, power will become negative. So I can write over here, this is equal to rho 2 by rho 1 times gamma minus 1. So this is one very important equation. Okay, so this is very important equation, because what it is doing, in majority of the situations we will be finding that pressure and temperature are actually the primary measurable properties. Okay, one can easily measure the pressure and temperature. Okay, so With the help of pressure and temperature, you can relate the specific volume and density for a calorically perfect gas, particularly for an isentropic process. Okay. Now, one question may come to our mind that why we always are considering over here the isentropic process, and that too when I am saying that in compressible flow we will be mainly referring to the reversible adiabatic process. Okay, so this is one important question. To us it may appear that reversible adiabatic situation may not be practically feasible. Okay, so because whenever we consider, we say that all practical processes are nothing but the of irreversible nature. They are having some sort of irreversibility associated, and achieving adiabatic situation is, though in some cases it is quite easy, but then also it is not that appropriate for majority of the situation, because you cannot stop for heat transfer to take place. Okay, but still I am actually focusing on this concept of isentropic process, that too with reversible adiabatic situation, and then many times saying that this is not much this is mainly used for all compressible flow problems. So the reason is that if you take, say, flow over a flat plate, okay, for the flow over a flat plate, you will be finding, I am not referring to the low speed flow, I am referring now to the high speed flows. Okay, so even if I take flow over a flat plate, so basically in compressible flow what we are having, we have say this one aerodynamic bodies, and flow is happening over the aerodynamic bodies. Sometimes we have flow through the nozzles and diffusers, etc. So majority of the times we will be experiencing the high speed flow. So in the high speed flows we will be finding that we will be having very thin boundary layer. So here this region over here is nothing but the region of boundary layer, and then majority of the flow we will be having outside the boundary layer. Okay, and we will also see that within the boundary layer we will be having presence of diffusion and all forms of irreversibilities. Okay, because what is the cause of formation of this boundary layer? The cause of formation of this boundary layer is nothing but the friction, viscosity of the fluid medium. So because of the viscosity of the fluid medium we will be having this formation of nothing but the boundary layer, and obviously friction is actually the primary cause of irreversibility. Okay, so we will be having the momentum diffusion because of viscosity. At the same point of time we can have some thermal conduction effects also. So any heat transfer or any diffusion of the momentum and irreversibility is taking place, I can say that in a boundary layer only all the irreversibilities are present. Okay, I have already written. So all the irreversibilities are present in nothing but the boundary layer region. However, outside the boundary layer region, if you see, everywhere my velocity is nothing but equal to the free stream velocity. And if you do remember, we can consider outside the boundary layer the situation of nothing but a viscous inviscid flow. So outside I can take a situation of inviscid flow. Okay, so when I don't have any viscosity outside, and moreover my speed of the flow will be so high that it will not be having, even if small temperature gradients are also present, then also it will not be having sufficient time for the heat transfer to take place. Okay, so though it may sound to us that the situation of reversible adiabatic or isentropic flow, corresponding isentropic flow is not something which is more practical, but for majority of the compressible flow situation, because irreversibilities are associated only within the boundary layer region, which is very thin and just adjacent to the aerodynamic body or the surface which we are considering. Okay, whereas away from that, whereas we are having the large portion of the fluid element. So here we have the large portion of the fluid element because this thickness of the boundary layer is very, very small. Okay, so here we have this large portion of the fluid element. There we don't have any viscosity dominant situation. So it means we don't have the irreversibilities, and if we are not having irreversibilities, then I can say the situation is reversible, and at the same point of time we will be finding that the fluid velocity will be so high, energy of the fluid will be so high that it will not experience sufficient time to transfer the heat, even if actually some small thermal gradients are actually present over there. Okay, so this is the reason actually that for majority of the compressible flow situations, considering reversible adiabatic situation does not introduce much errors. Okay, so assuming reversible adiabatic isentropic situation for majority of the compressible flow problems actually gives us nothing but the accurate prediction as well as the accurate analysis of the flow problems. Okay, now in this previous formulations I have used this equation Cp minus Cv equal to R. Okay, let's try to see from where this equation is actually coming. Okay, so we have come to know one important relation, H is equal to U plus PV. So if I do calculate dH, that will be equal to du plus PdV. Okay, before that, let's do one thing. Let's try to find out this particular relation, nothing but for a calorifically perfect gas. So for a calorically perfect gas, PV will be equal to RT. So let's replace this H is equal to U plus this PV I can replace with RT. Okay, now let's take dH. So dH will be equal to du plus RDT, and TDR makes no sense because R is constant. Okay, so dH, now for calorically perfect gas I can write dH equal to Cp times dt and du equal to Cv times dt plus R dt. So from here dt will cancel and Cp minus Cv will become nothing but equal to R. Okay, so this is the important relation. Now remember one thing, Cp minus Cv equal to R is applicable for calorically perfect gas. So this should be very, very clear to you. Okay, so this is applicable for a calorically perfect gas. Now if I say divide this equation throughout by Cp, earlier also we have seen, so I will get 1 minus Cv by Cp equal to R by Cp. So 1 minus 1 by gamma equal to R by Cp, or gamma minus 1 by gamma equal to R by Cp. So from here I can find Cp as nothing but equal to R gamma times gamma minus 1. Okay, so this is also important relation which we may use many times during our subsequent lectures. Okay, another relation which we can derive from here is Cp minus Cv is equal to R. So dividing throughout by Cv, so I will get gamma minus 1 equal to R by Cv. So from here R will be equal to, sorry, from here Cv will be equal to R divided by gamma minus 1. Okay, so these important relations for calorically perfect gas are actually very, very important, because as I told you that majority of the times we will be using nothing but the assumption of calorically perfect gas. Okay, so now let's try to see the next situation. So let's consider that how the forces act on an aerodynamic body. So what I am doing, I am trying to draw over here the complete three-dimensional profile of the aerofoil. Okay. So if I draw the complete three-dimensional profile of the aerofoil, you will be finding that above this also we will be having flow, and below this also we will be having certain amount of flow. Okay. So now let's consider that S is the total surface area of this one. So capital S I am using as a total surface area of this one. Okay. Then if I take a small element over here on the surface of this aerofoil, and let's consider this element is having surface area ds. So please don't confuse it with the entropy. So whenever I am writing this S, you will be finding I am little bit making it thick. So basically I am writing as a bold letter. Okay. So if this is my surface over here, then what type of forces you think because of the fluid will be acting on this body? Okay, now let me also fix the coordinate system. This is my x-axis, this is y-axis, this is z-axis, and say I have normal to this surface a vector which is n vector along the y direction, and I have say m vector along. What are m and n? M is unit vector along and n is, or let me not write over here x and y direction, let me call it as m is unit vector along the surface, and this is unit vector normal to the surface. Okay. Now these are my m and n vectors. So tell me what type of forces will act on this because of the fluid. So we know that because of the fluid we will be having nothing but surface forces over this. Okay, so majorly we categorize forces into two parts: body forces and surface forces. Okay, so body forces will be because of its own volume. Okay, whereas the forces because of the fluid will be acting at its surface. So the very first surface force will act is pressure. Okay, so on every fluid element we see some pressure is actually acting. So pressure will be acting in this direction. This is my pressure. Tell me, pressure is a scalar, vector, or a tensor? Scalar. Why pressure is scalar? Why? I am drawing it with some arrow. Okay. The point is, if you see the nature of the pressure, uh, fundamentally it is like a tensor. It is acting on some surface and then it is having some direction also. So fundamentally it is like a tensor, like your say sorry, stress tensor. But pressure is having two important characteristics. First characteristic is that it always acts normal to the surface, so it will be always normal to the surface. Second point is, second important characteristic, it is always of compressive nature. So it means it is always having unique direction. So because of its unique direction we refer it to be a scalar quantity. Okay. So as I told that it will be of compressive nature, so it must act to the body, and second point I told that it has to act normal to the surface. So if this is my n vector, parallel to this I am drawing actually the pressure. Okay. Similarly, I will be having some force over here. What is this? So say shear stress. If this is tau is shear stress, then shear stress will be acting parallel to the surface. Okay. So it means on this small element, if you find the forces which are acting, that is pressure, and pressure is acting on area, and it is having normal vector n. So I can write this ds surface as n times. Okay. Now see one important point. This pressure and normal vector, they are in opposite direction. So due to this opposite direction, I will put a negative sign over here. Okay. Then I have plus tau m into ds. Okay. Now if I have to calculate the force over entire body, then what I have to do? I have to find pressure at each and every point and stress at each and every point of this aerofoil on the top side as well as on the bottom side, and then I have to do integration of the entire force over the complete surface. So I can say that F will be nothing but equal to surface integral, and this closed circle I am putting because top side and bottom side is making a closed surface. Okay, so this surface integral of df. Okay, so this will become equal to surface integral of minus p n ds and plus surface integral of tau m to ds. At this s I am referring to the complete surface. Okay, is this point clear? So I can say that these are the forces, this is the net force which is acting on this. Now we know that because of this there will be some reactive force. Okay, so see the direction of that reactive force is, resultant reactive force is F. If this is the F force which is acting on fluid because of this body, then this body fluid will produce equivalent reactive force in the opposite direction. So say this is the actually equivalent opposite force F. Now this F will be having two components. One component will be in x direction. This is parallel to x axis. So in x direction the component is known as drag, and in y direction it will be having one component. In y direction the component is known as lift force. Okay, so now from here, as I told you that this m vector and n vector, these are not along x and y direction, these are along the surface. Okay, and many a times you can see that, say here it may appear that m and n are parallel to x and y, but in many situations if your say airfoil is at some angle, then obviously m and n will not be parallel to the x axis. Okay, so remember this point. In this figure it may appear m and n as parallel to x and y, but in reality one is parallel to surface and another is parallel to normal to surface. Okay, but in the definition of, whenever we will be referring to the definition of drag and lift, don't confuse it with m and n. So drag is not parallel to n, drag is parallel to x direction. Okay, so parallel to the x direction we are calling as drag force, and normal to the in y direction whatever the force we are having, that we are calling as nothing but the lift force. Okay, so it means m and n can be at certain angle to drag and lift force. This point is clear? So drag will be always in x direction and lift will be always in y direction. Okay, so by considering this I can simply say that whenever we are having lift and drag formulation, we will be finding in majority of the situations that viscous component. So this is the viscous component of the force, resultant force. Viscous component of the resultant force contributes very less to the lift force. Okay, so lift force is mainly contributed because of the pressure component of the force. So that's why I can simply say that my lift force will be nearly equal to y component of surface integral minus p n ds. Is this point clear? Because viscous force does not contribute much to the lift force. That's why I can simply say that lift force will be mainly because of the pressure force. Okay, so y component of pressure force, because pressure can also be at certain angle to the surface if surface is actually tilted. Okay, so that is the reason we are say writing over here the y component. Okay, whereas if you calculate the drag force is contributed because of both pressure as well as the, so I will be having x component of minus p n ds plus x component of tau m ds. Okay, now remember one thing, this we study in our basic fluid dynamics also. This is called as nothing but the pressure drag or form drag, and this second one is called as viscous drag or skin friction drag. Is this one clear? So this is something which we study in our fundamental fluid dynamics as well. Okay, so we have pressure drag and form drag, and we have viscous drag and skin friction drag. Okay, now one important point, just now I was telling you in the lecture that we will be considering reversible situation. So if I consider the reversible situation, then what will happen? For majority of our compressible flow problems, I told you just now that we will be considering nothing but the reversible situation. So if I consider reversible situation, then what will happen? Yes, this viscous drag will vanish. Okay, whereas viscous forces contributes to significant amount into the drag force. Okay, so it means that if I consider the reversible situation for analyzing the compressible flow problems, if I consider the reversible flow situation, then I will not be able to predict accurately. Yes. Is this point clear? What I said? I told you that majority of the time we will be considering the reversible situation, and why we will be considering reversible situation, that also I explained. Okay, so as reversible situation vanishes the viscous component of the force, that means the skin friction drag, which is having major contribution in the overall magnitude of the drag force. So that's why we will not be able to accurately predict the drag force. However, these reversible assumption may work for a very special kind of objects which are called as supersonic slender objects. If you are having very long slender type of geometries, okay, and these are nothing but having some supersonic flow situations, they are actually the major contribution of the drag comes from the actually pressure drag. Okay, so what I am referring to, for example, if you have some slender object like this, okay, so in this slender object you will be finding that if flow is taking place like this, then shear will find very minimal area. Okay, majority of the force will be because of the accumulation in the form of pressure. So if you have very high speed flow and then you are having actually this very long slender object, then the component of the viscous force will be very less in the total magnitude of the drag force. So there we may use actually the reversible situation for predicting the drag force with sufficient accuracy. Okay, is this point clear? Okay. Now after this, whenever we will be referring to the situation of compressible flow, the important point is we have to determine nothing but the governing equations, because unless or until we are not having the knowledge of governing equations, then we cannot we cannot analyze our flow situation. Okay, so very important point, before doing any analysis we must know about the equations that govern the dynamics of the fluid flow. Okay, so when we do calculate governing equations, we can take a different type of formulations. So one of the formulation is that if I have, say, fixed finite sized control volume, another I can have moving finite sized, then another situation I can have fixed infinite small control volume, then moving okay. So we can have four types of situations. So let's one by one try to see the each situation. So in this situation we have a finite sized control volume where this boundary is fixed, it is not moving. So fluid is entering from, say, this side, it is passing through the control volume and then, say, leaving from certain other boundary. Okay, but this fluid element is actually not moving. Whereas in second situation, fluid cannot pass through this because this is nothing but an entity of fluid which is moving in a flow. So this fluid element itself is actually moving in the flow. Then in other situation, I have a fixed infinitesimally small control volume where also fluid is entering from other side and leaving from the passing through it and then leaving. It is fixed in space, and this control volume itself, it is actually moving in the flow field. Say after some time it will be somewhere over here. Okay, so its complete fluid element is actually moving. So these type of four control volumes are actually fundamentally taken to derive the governing equations for fluid flow. Now when we consider the finite size control volume, in this what can happen, there can be variation of property within the control volume. Because if you have, say, if you consider this large sized room as your control volume, so you may have, if you are at this point, say you have more density, at other point you have less density. So in the finite sized control volume there can be variation of property within the control volume. So this is the reason when we do calculate the governing equations for finite sized control volume, we get the equations in the form of integral form. Okay, when you apply finite sized control volume, then we get equations nothing but in integral form. The reason is very clear, just now I told you. There can be variation of property at different locations. So if you have to account for the complete property, the complete quantity for the entire control volume, then I have to do integration over that finite sized control volume. So that's why from these two, what we obtain is nothing but the integral form of governing equations. Okay, and below these we obtain nothing but the differential form of governing equations. Now once again, remember one important point. I am saying it as infinitely small. So what do you mean by infinitely small? Infinitely small can be, you go up to very small length, say 10 to power minus 10 meter size. If you go to that much small size, there what you will be finding that continuum will not be valid. Okay, there you have to account for the individual molecular motions. So what do you mean by this infinitesimally small? The meaning of this infinite small control volume is that we will be selecting suitably small control volume, so that for this control volume properties are yes, continuous or fixed. Okay, so for this control volume you can designate, okay, you have some density rho. So this is so small that within this control volume variation of the property is actually not taking place. Okay, so once you are selecting, so please make clearly the distinction between size. You should not go to very small size where actually your continuum is vanishing and molecular effects are becoming important. You have to restrict to some small size where continuum is valid. It means you have sufficient number of molecules inside this which can give you the idea of, which can satisfy the idea of continuum. Okay, at the same point of time, you should have such a small size that property is not varying for this one. Okay, so say this control volume is having fixed density rho. Okay, within the control volume density is not changing. So this is what we call as infinitesimally small, and whenever we use this formulation, then we get nothing but the differential form of the governing equations. Out of the integral and differential form of governing equations, if you have to consider the more generic form, then actually differential form is called as nothing but the more generic. Now can you give me the idea why it is called as more generic form? Why differential form is called as the more generic form of governing equation? The reason is, if you have to use the integral form, that is applicable for as a whole for the complete control volume. That is, you cannot satisfy integral form at each and every point of the control volume. Integral form will be applicable for the entire control volume. Whereas if you consider the differential form of equation, differential form of equation can be applicable for at each and every point within the control volume. Okay, so it means if you are having some discontinuities in the properties, that can be taken care of by the integral form, because it will be having, it is applicable for the integration for the complete control volume. Okay, but this is the more generic form, differential form, which is applicable for each and every point of the control volume. If you take differential form of the governing equation, you can satisfy at this point, you can satisfy at any point in the control volume, it can be applicable and it can be made satisfied. Whereas the integral form is applicable nothing for the complete finite size control volume. Okay, so this is the reason that differential form is called as actually the more generic form. Okay, another important idea is, so I have told you two things, I have already explained you, that in first case we will be having the finite sized control volume, and this will give me the integral form of governing equation. In second case, if I select a control volume such that it's sufficiently small where property variation is not taking place, then I will be obtaining nothing but the differential form of the governing equation. Then third important thing where we have to find the governing equations is when our continuum is not valid. If continuum is not valid, then what we will be doing? In the domain we will be having, say, finite number of molecules. Okay, number of molecules will be very less. Then we have to write the governing equation for each molecule. Each molecule or particle. Okay, and if we solve the behavior of each of the molecule and then do some statistical averaging like we do in case of statistical thermodynamics or statistical mechanics, then actually we will be able to predict the behavior of the overall system. So you can see that from fundamental perspective, actually this is the most fundamental. Here actually you are trying to uh, find out or analyze the motion of each and every molecule present in the flow field. Okay. However, in continuum level, what we do, there can be a variety of molecular activities. We just consider the averaged properties and then we try to analyze the average flow situations. Okay, so this is the most fundamental where molecules are to be considered. But molecular, particularly these interactions in this course of compressible flow, we will not be doing. So we will be only dealing with the mostly with the integral or differential form of the governing equation. So I will stop now, and in the next lecture then we will be starting with the this derivation of the governing equations. Okay.